In this video, let's talk about log properties. There are many of them, so let's talk about them in detail. For example, I can count about up to 8 properties of log functions. What are they? Well, for example, log base a of 1 is equal to 0. Well, that kind of makes sense if we translate it into exponential form, which means it's a to the power of 0 is 1. And that is actually true. So that's why we know that the log of 1 is 0. Well, the same thing happens with log base a of a, that's actually 1. Well, it makes sense again because a to the power of 1 is equal to a. So again, it checks off. What about this one? Log base a of a to the x is equal to x. Well, if we translate it to exponential form, then we know a to the exponent of x is equal to a to the x, which sort of seems redundant at first, but it is true. And there is actually a deeper reason for this property. What it means is that log and the exponential, as long as the bases are the same, they are inverses of each other, which basically means they cancel each other. If first you raise x to the exponent, then you take the log of that function, then you get back to the original x. So they cancel. And this is the reason. Every property of the logs has some sort of exponential property that's behind it. What about this one? A to the power of log base a of m, for example, or any value over here. Well, again, for the same reason, because the exponential y equals a to the power of x and the logarithm y equals log base a of x are inverses, which means they cancel each other. So the result is m, or whatever the expression is that's over here. That would be the result. Okay, let's talk about other properties. These take quite a little bit more of justification, but the log of the product can be separated as the sum of these two products. This is the property, if you recall, if we have the same, for example, exponent, and we have a product of exponents. Well, what happens to that product? We add the exponents. It's kind of the same idea. If log is the exponent, well, the log of the product, sort of like the product of the exponents, becomes the sum of two different logarithms, which means you see how the exponents become the sum. It's kind of the same idea. We have a similar division property. Again, the same kind of property makes sense if we divide two exponents. It simply becomes subtraction. It's the same kind of idea. The log of the division is equal to the subtraction of two different logarithms. Now be very careful. We cannot do the same thing, for example, for logarithm of the sum. That we cannot separate. And also the same thing for the subtraction. So we have to be very careful not to be able to separate. And here is one more property, which is log base a. This doesn't have to be the same base, but for example, any value that has another exponent, for example, x to the exponent r, that exponent can actually come down on the front of the logarithm, so it becomes r times log base a of x. And again, we have a similar exponent property that we have, which is exponent raised to another exponent is the same as the product of the exponents. So if the log and this r are both exponents, this becomes a product right here of two values. Okay? What else we have? We have something that's called change of base, which basically it means that the log of base a of m, or anything, or any expression, can be changed to log base b of m divided by log base b of a. So now a becomes the argument and it's no longer a base. Why would we want to do that? Well, if we want to, for example, input logarithms in most common calculators would have common log, which basically means it's log of base 10, or ln, which means it's log of base e. And we can translate now any logarithm in terms of either one of these logarithms, and we'll be able to actually input it in the calculator. So what can we do with these properties? When we start solving equations, that will really become helpful. And of course, equations come up in real life applications, and there are a lot of applications with exponentials, as we'll see later. And of course, each application may have its own equation associated with it, so it may help to know how to work these properties to be able to evaluate different expressions and equations. Well, sometimes we start with a single expression and we want to break it up. Well, as you can see, it's actually x times x minus 1, and it's a product. So we can use property 6, for example, to be able to break it up. So it actually looks like ln of x plus ln of x minus 1. Now this we cannot break up any further, so we stop right here. Now let's take a look. What about something like this? Log of square root of x squared plus 1 over x plus 3. So it's something more complicated. Well, first of all, it's a division. So we can actually break it up. Let's take a look. Well, the first step may be to rewrite the radical as the exponent of 1/2. We're going to need this a little bit later. So that's an exponent. We actually cannot, it may be very tempting to reduce the square right here, or the 1. But because of the plus, we actually cannot reduce it. It's irreducible, similar with the logarithms. So, again, what can we do? We can break up as a subtraction, as we mentioned, the division, and then this exponent of 1/2 can actually come down, and this is the final expression. We have 1/2 times log of x squared plus 1 minus log of x plus 3. Now note, there is still an exponent of x squared that's left, but because of the sum, we cannot actually break it up any further. So be careful not to go further than necessary. This actually would be the final answer. So let's take a look at another example. What about what if we want to work backwards? What if we want to start out with the expression in condensed form? How would we compactify it in the single form? For example, log base 2 of x plus log base 2 of 7, well, it's the same thing as log base 2 of 7x. So this one was fairly simple. What about something more complicated, such as 1/5 of log base 2 of z plus 2 log base 2 of y? Well, the first step, since we're working backwards, may be to bring up the exponents. So this 2 becomes y squared. Then we can actually combine this plus as a product, log base 2 of zy squared. And the last one, this 1/5, actually we'll leave it to the end for this one, because that can now come up as the exponent of 1/5. And we can leave it like this, or we can rewrite it as the 5th radical. Let us do one more example. What about 2 ln x minus 1/2 ln of x squared plus 1? Can we compactify it as a single expression? Well, yes, again, we can bring up the coefficients, which become exponents. So here they are. What about the next step? Well, we can actually do it in a single step. The minus is a division. We know that 1/2 is actually a radical, so it would be x squared divided by radical of x squared plus 1. Now, typically we would rationalize this, but actually for now we will stop here, as we're just illustrating logarithms. All right. Let's talk about change of base just a little bit more. Here is the overall change of base, and then again, it helps to have either in terms of log base 10 of m divided by log a, or ln of m divided by ln of a. So we can simply use this. So let's take a look at one example. What about the log base 2 of 5? How can we put this in a calculator, for example? Well, we can, for example, use a ln. Let's say a ln of 5 divided by a ln of 2, or we could have used log base 10. So it could have been log base 5 divided by log of 2. Actually, they're both base 10. So either one should give you the same answer if you put in a calculator. And they both should be 2.322. And don't forget to close the parentheses, otherwise you will get a different answer. It should look exactly like this. And mostly properties require a lot of practice. And so make sure just practice a few of them and you'll be able to master them. That's it.